All right, let's zip through these things. All right, number one, how many moles of aluminum are in 54 grams of aluminum? So we need to go from grams to moles. When we go from grams to moles, I've got 54 grams of aluminum. I need to divide out grams of aluminum and turn that into moles of aluminum. Moles to grams, we get that off the periodic table. It is 1 mole. Aluminum, I believe, is 26.98. So 1 mole of aluminum is 26.98. That's the molar mass on the periodic table. So I take 54, divide it by 26.98, and I'm going to get right around A on that one. So number one should be A, 2 moles. Number two, asking how many atoms are there in a certain number of grams. So as before, let's start with, it's too big, 15 grams. So I want to change out the grams, and I need to turn those into moles. And then I'm going to divide out the moles and turn those into atoms. So grams and moles, again, that's going to be in our periodic table. 1 mole is, let's go check on sulfur, 32.07. And then the relationship between atoms and moles, that is Avogadro's number. So 1 mole is 6.02 times 10 to the 23rd. So I'm going to take 15. I'm going to divide that by 32.07. I'm going to multiply that by 6.02 times 10 to the 23rd. Remember on our calculators, that's generally 6.02. And then we're going to hit the second button to make the EE sign come up. 15 divided by 32 is approximately a half, so about half of 6 is going to be about 3. So I believe our answer on this one was C. So 15 divided by 32.07 times 6.02 times 10 to the 23rd should give us the answer C on that one. Number three, we're going from grams to atoms, which is the reverse of the previous question. Right. Sorry. So we've got atoms, and we're trying to end up at grams. So I need to cancel out atoms. I can turn atoms into moles, and then I need to cancel out moles and turn that into grams. So my number that I would start with, instead of me rewriting it, I'll just highlight it there. 9.03 times 10 to the 23rd. My relationship again here is the Avogadro's number relationship. So 1 mole is 6.02 times 10 to the 23rd atoms. And then my relationship here is the molar mass. So I need to get that off the periodic table. 1 mole of copper, let me find copper, 63.55. So in calculator, 9.03 times 10 to the 23rd divided by 6.02 times 10 to the 23rd times 63.55, which is on top. And that should give us approximately B, which is 95.3 grams of copper. Number four, at grams of boron, want to go to atoms of boron. In order to do that, we need to make a stop at moles. So I've got grams. Can get rid of grams. Can't go directly from grams to atoms, but I can go from grams to moles, and then I can go from moles to atoms. So we have 88 grams to begin with. Grams to moles is my molar mass. So 1 mole of boron, again, let's go to the periodic table. Boron's number 5, 10.81. And then the relationship of atoms and moles is that 1 mole is Avogadro's number, 6.02 times 10 to the 23rd atoms. In the calculator, start with an 88, divide it by 10.81 on the bottom, and then multiply it by the 6.02 times 10 to the 23rd on top. Should give us D, 4.9 times 10 to the 24th. On number five, it's asking how many moles are in a certain number of particles. This one will really just need to divide by Avogadro's number, so I'm going to take that. And a mole again is 6.02 times 10 to the 23rd particles. So if I take that number and divide it by that number, that should tell me how many particles I've got, or excuse me, how many moles I've got, which in this case would be about 4. Scroll down to the next page. Percent composition. So I want to know what percent of this compound is made up of magnesium. So this one's a little bit more involved. Again, if you want to think about this as a pie chart, the whole pie is the magnesium MgPO4. So the pie is made up of magnesium, phosphorus, and oxygen, and we're trying to figure out what piece of the pie is magnesium. So what we need to do for each of these is, first of all, write down how many of each we've got. This may not be the only way to do it, but it's like how I do it. We've got 3 magnesiums. There's 1 phosphorus in the parentheses, but there's 2 sets of them, and there's 4 oxygens times 2. So that's the number of atoms that we've got. I need to multiply each of these by the atomic mass. So for magnesium, it's 24.31, oxygen 16, and phosphorus is 30.97. We get answers for each of these, because again, I'm trying to find out how much does my whole thing weigh. 3 times 24.31, 72.93. 8 times 16 is 128, and 2 times 30.97 is 61.94. I want to add all those together. It's going to give me 262.87. So this is my total. Remember, percent is always part out of the whole. So this is the number that would be on the bottom of a fraction. So we want to do part over the whole or part over the total. So that is my total weight. So 262.87. The question was, what is the percent composition of magnesium? The magnesium of this weighs 72.93. Put these in the calculator, turn it into a percentage. So 72.93 divided by 262.87, turn that into a percentage. And the answer for number 6 should be C, 27.74%. Number 7 is a little bit more of a reasoning type of question. It's just asking which sample, 1 or 2, is correct. The main thing we need to figure out here is on the periodic table, what's the molar mass of each one of these? So sodium is approximately 23. Helium is approximately 4. And so if you had 2 grams of helium, 2 over 4, you'd have 2 grams out of 4 grams. That would be half of a mole, because 1 mole of helium should weigh 4, 1 mole of sodium should weigh about 23. And so some of the information in sample 1 is not really correct. Again, because 1 mole of sodium would not weigh 12 grams. 1 mole of helium would be 4 grams. So a half mole of helium would be 2 grams. Also, a half mole would be half of Avogadro's number. This is all of Avogadro's number. So that's actually correct. That's the right number between moles and atoms, but so is this. So half of a mole would be half the number of atoms up there. So everything about number 2 is correct. And so that's why if you go through and read B ends up being our right answer, because sample 2 is the one that's described correctly. And the reasoning is because half the atomic mass would be half of a mole. And that's what half of 6.02 times 10 to the 23rd is. All right. Number 8, we're trying to find the percent composition of carbon dioxide. So the relevant info here is I've got 200 grams. And so 200 grams is my total. And I'm trying to figure out what goes on top, like how much carbon dioxide is going to go on top up here. So if I've got 0.3 moles, I need to figure out how many grams that would be. And so if I've got carbon dioxide, carbon is 12.01, oxygen, thought I worked this out somewhere so I didn't have to do it again. Again, carbon 12.01, 2 oxygens, 16 and 16 is 32. So my total of oxygen, if I add that up, is going to be 44.01. So 1 mole would be 44.01 grams. I don't have that many, so I've got 0.3 moles. So I would multiply that by 0.3 to get the correct number of moles that I would have here. To make sure if we're on the right page with things. So I got 44.01 times 0.3. That's 13.2 grams. what do I do with that? Notice that's a choice up there, so you could be wrong about that. 13.2 needs to go on top of this fraction. So 13.2 divided by 200, that's going to get us our 6.6 because we would turn that into a percentage. So again, we're looking at what is the percent composition. So out of the 200 grams total, how many grams of it was carbon dioxide? And we just simply needed to convert our moles, 0.3 moles, into the correct number of grams on that one. Almost done here. All right, SF6 has a molar mass of 146.07. Student has a mass of 235.7. That's more than 1 mole. So I need to find out how many moles that is. So 235.7 divided by 146.07 is going to tell me how many moles this should be. And that's approximately 1.61 moles. And then how many particles would that be? Well, I just need to multiply that by Avogadro's number. So A and C are both the right number of moles, but 1 mole is 6.02 times 10 to the 23rd. This is more than 1 mole, so I should have more than 10 to the 23rd. So that's going to eliminate this one. If you took your 1.6 and multiplied it times Avogadro's number, we should get that number, which is going to be A. So our first step was to figure out how many moles is that. So if we know how many moles that is, then we're going to multiply that times Avogadro's number, and that's going to give us the number of particles we need. Number 10 is an empirical formula question. Empirical formulas are ones that can be simplified into the same ratio. So the ones that can be simplified, I can't change this one any. There's a 1, there's a 3, there's a 1, and a 1. I can't simplify this one anymore. However, number 3, 6, 12, and 6 can all be divided by 6. So I could simplify it into CH2O. In other words, if I divide the 6 by 6, I get a 1. If I divide the 12 by 6, I get a 2. And if I divide the 6 by 6, I get a 1. So the empirical formula of C6H12O6 is CH2O. Same thing for number 4. I can divide each of these numbers by 2, and 2, 4, and 2 are going to reduce to 1, 2, and 1. So 2, 3, and 4 are the ones that are going to have the same empirical formula. And the reasoning why is because they're going to be able to kind of simplify down into the similar ratios. And so the best answer for this one's going to be, excuse me, it's going to be D because of the reasoning that is on. So C and D both have the same right answer. The reasoning on D is a little bit better because the simplest ratio is going to be 1 to 2 to 1. And is that it? Nope, one more. So this very last one, the question is, what's up with this number right here? So sample 1 is FES. That's a 1-to-1 ratio. So the moles are the same on this. So if I divided each of these by 2.7, it would reduce to 1.1 to 1. Sample 2 is Fe, one iron, 2 sulfurs, and if you look at your ratio, there's 4 moles and 8 moles. Well, this is twice the number of moles as we have here. And so that's why we end up getting the formula of FeS2 is because for every one of these, I need 2 of this one. Up here, for every one of these, I would have 1 of these. So what's going on here? This number is 1.5 times as big as this one. So in other words, if we divided both of these by 2.6, you get a ratio of 1 to 1.5. So we can't have formulas of the 1.5. We can't write FES 1.5. We want to make them into whole numbers. So the easiest way to do this would just be to double the numbers. So instead of having a 1 and a 1.5, double both of those, and it should turn us into a 2 and a 3. So the best formula we could put together for these number moles will be Fe2S3. And so the right answer on this one ended up being A. So that's our correct formula. There's a correct formula down here as well, but but the better reasoning is about multiplying your numbers to get to whole numbers. So we don't want to round the digits to get to the nearest whole number. We want to multiply numbers to get to the nearest whole number. There you go.